Vectors look like this. I'm going to teach you right now. I'm going to do something, you watch, and I'm going to ask you a question about it. 1, 2, 3, 4, 5. Tell the person beside you how far I went. Who says 1? Who says 5? Nobody says 5. Oh, Olivia says 5. You're both right. You're all right. I went, yes, 1 step forward from where I was, right? Barca, right?
Yeah.
So Barca says I'm 1 step forward from where I was. That is displacement. Everyone say displacement. Displacement is a vector. It's about your position. It cares about direction. 5 is just how far I walked. That is called distance. Everyone say distance. Distance is a scalar. A vector, other than being the best cartoon villain of all time, includes magnitude and direction. An example of a vector is as we said, displacement. Velocity is another one. Yep. I would. Acceleration is a vector. Force is also a vector. Can you think of something that doesn't care about direction? A variable in physics that is a scalar. One of them I just told you. Very good, Bonnie, thank you. Distance is a scalar. You've driven in a car before, probably. The little thing that rolls around, or your little digital readout, it tells you how far you've gone. Is that telling you displacement or distance?
Distance.
Good, yeah. Joe says distance. How did she know that? Maria? Yeah, it just records how far you went. If it did displacement and you drove to the mall and you came back home, what would it read? 0. That's right, Bonnie, that's right. So if I ask you on a quiz, hint, hint, nudge, nudge, wink, wink. If I asked you on a quiz, Yara runs around the track, 400-meter oval track in front of the school, and she runs it in 10 seconds. What is her average velocity? Close. What did Irene? Irene, I'm sorry. I'm gonna use what you said as an object lesson. Why is what Irene said wrong?
Because you said it.
You're on video saying that. That's harsh. That's harsh.
Said straight to the
Irene, do you know why?
I didn't know why.
Can you spot your own mistake? Does anybody know the right answer? Maria. Ah, okay. So Irene's average velocity would be 0. Why? She ran around the track. She burned a bunch of energy. It was hard. How could it be 0 velocity?
Because it was like around the track.
Yeah.
To go back to the track.
Exactly. Very good, Bonnie. She ran around the track and came back to where she started. So her distance, now what Irene said was distance over time, which is something. It's not velocity, it is speed. Speed is the scalar version of velocity. Thanks, Anthony, I appreciate that. So speed doesn't care about direction. Doesn't matter that you went around and you came back to where you were. It's just how fast you were going. That's what the thing in your car measures as you're driving along. When you're on the freeway, if you do a turn or whatever, you come back the way you came, it still says you're going 60 kilometers an hour. The velocity, though, would be maybe negative 90 or 90 kilometers an hour west or something like that. Okay. This is maybe a controversial one, but I will also say time. Really, because it only goes in one direction for us, as time is always moving forward. So time we think of as a scalar, and energy we think of as a scalar as well. My board is like squeaking. Okay, so you have vectors and you have scalars, and we're interested in vectors. So, I'll go over here as well. Can we see this board? Thank you, Mandy. If you are flying in an airplane and you're flying at 800 meters per second, that would be really fast. Let's say 200 meters per second. That's the speed that the plane can fly when the air is still and things are normal. Okay, but you fly your airplane into a wind. Let's say we're flying to the east. You guys know which way east is? Yeah, east is that way. Thank you, Mateo. Mountains are north. This is east. That's where the sunrise is over there. Right? You're flying your airplane into the wind. So let's say you have a 30 meter per second wind to the west. What would the ground speed of the airplane be? In other words, if you're standing on the ground looking up at the airplane, it's flying with an airspeed of 200 meters per second that way, but the wind is coming back towards you at 30 meters per second. What would you see happening? Any ideas? What do you think intuitively? Just take a guess.
170 meters per second.
Give Bonnie a golf clap. Yeah, because if you're flying this way and the wind is blowing against me, relative to the air, I'm still going 200. I feel fine. I'm all good. But all of the air is moving this way at 30 meters per second, right? So when you stand on the ground and you watch up, you see the sum of the two. This is called vector addition. So we're going to add those vectors together, and what we do is we draw the vectors on a page. This is a very simple example, but it's good to go through it because it gets much more complicated. So the first thing you do is you draw the vectors as arrows, and you draw them tip to tail, because that's kind of how it goes in real life. So if you were watching me walk, you'd say 1, 2, 3. You would have said 3 meters this way, but then you've drawn an arrow 2 meters back. And to get the result, we call it a resultant vector. Everybody say resultant vector. You start at the beginning, where you started, and you draw to where you finished. And that is our VR, our resultant vector. And you can think of this as, because these are in opposite directions, you can think of this as positive 200. This is negative 30. When you add them together, you get 170 meters per second, as Bonnie aptly calculated. This would be positive. So which direction is this? This is going to be east, yeah. So we just put the directions in square brackets. You don't have to worry too much about that, but it's just kind of how we do it. Yes, Malou.
What's the symbol or letter right next to the V?
This,
Yeah.
that's supposed to be a little r
Oh, okay.
for resultant. It's like a subscript r. Good question. Okay, so let's go back to this board here. So that's kind of the concept of vectors in a nutshell. As you could guess, IB problems get a little more difficult than 200 minus 30. So let's talk about a river now. Let's draw a river. Oh, I'm running out of blue. Some little waves here, maybe a fish. So you have a river flowing. Let's say that the river is flowing. Do you want it to flow to the right or to the left? Right?
Left. Left.
Who wants left? Who wants right? See, you guys are out. No bullying, no cussing.
Yeah.
That's super bullying.
That's on camera too. I'm taking this to court.
Yara, how fast do you want the river to go?
100 miles.
No, that's too much. Let's say 10. And let's say east. So the river is flowing 100 meters per second east, okay? Who's your favorite celebrity? Or who's your least favorite celebrity?
Jack Doherty.
Jack Doherty? I don't know who that. Oh no, I can't do that. I gotta keep it apolitical. That was a good one. Who's Jack Doherty? Who's that?
He's the guy who films pranks.
He filmed what?
He films pranks, but he's like not a good person.
He filmed what?
He films pranks.
Oh, he films pranks. Okay. Okay, so I don't even know who that is, but we'll call him.
Do you want a picture?
No.
No, please, bro.
Sure, Jack, whoever he is, he's gonna jump in the river and swim. But let's say is he a strong guy?
No.
No? Okay, let's say he's swimming in the river. What kind of hair does he have? Spiky, short, long, big afro?
Fridge.
Fringe? Fringe. Like this?
Like blonde fringe.
Like that?
Yeah.
Okay. Jack is swimming, but he can only swim 2 meters per second. West.
Jackson.
If we're all here
It's Jackson.
watching, turn to the person beside you and tell them what we are going to see him doing in the river. Okay, what are you gonna see? Mateo.
He's gonna go 8 meters per second east.
East. But he's swimming west. Shouldn't he be going west?
The wind is stronger.
The current is strong. Give Mateo a golf clap. Yeah, so even though but is he even gonna be swimming?
I think he's borderline.
Like, is his swimming doing anything?
Yeah.
Yeah, it is, right? Now, the river here's the river. It's moving to the west. All the water in the river is moving this way, right? So he's still moving 2 meters per second relative to the water. But the water is moving past us at 10. So he appears to be moving. So if it's like this, you have the river. And let's say the river is plus 10. Let's say this way is plus. And he swims at -2, let's say. What's my resultant vector? 8. Positive or negative? Good. So you're going to say my VR, in this case, equals positive 8. So Matea's absolutely right. You're going to see him moving to the right at 8. Right? Okay. Now, I'm sorry. It's going to get more difficult than this. Barca,
Yeah.
how wide is the river?
Do I say?
You can pick.
Let's go 6 meters.
6 meters, that's not very wide. Let's say the river is 6 meters wide. That's fair. And let's say, yes, Malu. Yeah, go ahead. Let's just say that Taylor Swift is with us, okay? And she's gonna jump in the river. She's here. She's getting ready. She's, life of a showgirl. She's gonna jump in the water, and she wants to swim across the river. I don't know. What would Taylor Swift want? A Grammy. That's a good one. Okay, so there's a Grammy over here. What does a Grammy look like? There's a trophy. I don't know. There's a Grammy. I'm a physics teacher. I don't know what these things look like. Kanye's nowhere in sight, so she's gonna be able to get it. But she has to swim across the river, right? Wasn't that what happened? Didn't he take it from her or something?
No. She intercepted.
Yeah, there was something like that. Anyway, she's gonna jump in the river, and she's a pretty good swimmer. Okay, so she can swim at, let's say, 4 meters per second. She's gonna jump in and she's looking at the ground. She's gonna swim straight across the river. If she points herself straight across, is she gonna get to the Grammy?
No.
Show me with your hand. She put your hand this way. She jumps in the river, but where does she go as she swims? She's gonna end up drifting that way, right? So here's my question. I'll give you a minute to figure it out. How far downriver will she be from the Grammy when she gets across? Well, you can't say that. Take a minute, figure it out. Mateo, what'd you have?
15.
Let's give him a golf club. Yeah. How many of you got 15? What was your name? Kazra. Remind me to change you on the attendance list. Kazra, tell us how you got it.
So I divided the width of the river by how fast you swim. So 6 divided by 4, which is 1.5.
So this is what Kazra's doing. He's saying this is constant velocity. So he's saying V equals D over T. But what he's going to do is he's going to get the time it takes for her to swim across the river. Okay. So he's moving this around and saying that T equals D over V. And he's saying, okay, the distance is 6 meters. Divide by 4 meters per second gives you
1.5.
1.5. So it's going to take her 1.5 seconds to get across the river, okay? If it takes her 1.5 seconds to swim across, what's happening while she swims? while she swims straight up, what else is happening? Yeah, Yara's going like this. The river's pushing her all that time, right? So how far down the river does she get before she gets there? 15, because the river's pushing at 10 meters per second and it's pushing for 1.5 seconds. So up here, you say D equals VT, and that's 10 because the river's at 10 times 1.5 seconds. So the whole time she's swimming, the river is pushing her that way. And so it's going to be 15 meters downstream when she gets to here. Okay. Now if I draw those vectors, I have, this was 4 meters per second upward, and my river is 10 meters per second. And I'm sorry, but the resultant vector is not up or sideways. What does it look like? It's going to be this way, right? If we say this is our angle theta, you have to be able to tell me that angle. So we have to go back to trigonometry. Joe just like made a lemon eating. Trigonometry. How many of you remember trigonometry? Long gone? Have you learned it this year? Are you going to learn it this year?
Last year.
Yeah, we learned it last
You learned it last year. Okay. What's the saying for trig? You remember SOHCAHTOA? So is sine, opposite over hypotenuse. I will post a trigonometry review. So if you're the one sitting there going, I don't know what they're talking about. I'll post a little review of trig. It'll be fine. But it's like this. And it all comes from that triangle of if this is theta, then this is opposite, adjacent, and hypotenuse. So we can go through, but you're gonna have to learn trig a little bit. Okay, tell me this theta. Go. You'll need a calculator. If you have a graphing calculator, make sure it's in degree mode. Who here has a graphing calculator? Okay. Who here has a calculator? Any kind of calculator? Okay, get it up. I want to see your calculator.
You're actually
Annie, what two sides do we have? What side is this one? This is the opposite side because it's across the angle, right? It's across the triangle. So this is the opposite side. What side is the 4? This is the adjacent side. And what's this one? This would be the hypotenuse, right? So we have the opposite and we have the adjacent. So which one are we using? So or ka or toa? We're going to use toa, which is tangent, right? When you're finding the angle, you have to do the inverse. So we go inverse tan of opposite over adjacent. So we go 4, is it 4? 10 over 4, sorry. And that will tell us our angle theta. Theta is that Greek symbol. 68. Is she right? Should I check?
Probably.
Okay.
No, I wouldn't trust it. I skipped all the decimals.
68. You did it. Okay, that tells you the theta. Okay. Question for you. If this is the last question I'll give you, and then I'm going to turn you loose because Mateo and I gotta watch a baseball game. If Taylor wants to swim, but she actually wants to hit the Grammy when she gets across, is there a way for her to do that? Kazra?
She just go like the opposite way of the current.
Okay, so she's gonna have to, she can't swim straight across because she's gonna get pushed, right? So she's gonna have to point herself against the current, yes? But she wants to be able to move straight across. So my question to you is, what is the angle she has to swim at this way in order to get straight across the river? Yeah,
68.
good guess. Wrong.
Another way though.
It's not. Think about it. Draw the vectors on your page. It's tricky. That's everybody thinks that, right? We intuitively go, well, we just like flip this around, right? But it's not quite. It's a little bit different. It's similar, but. Draw the vectors on your page. Try. So what's different about that triangle? What are we trying to get? Before we swam straight across and the river pushed us this way, right? So our resultant vector was the hypotenuse.
Oh, you're right.
But this time, where do we want our resultant vector to be? We want the resultant vector this time to be straight up, right? So how do we draw our vectors so that the VR is vertical? How are we going to do that? Oh, wait a minute. I don't think we can do this. She can't get across. She'll never be able to get across.
Are you saying she's too?
No, she can do anything. What's how fast did I say she could swim?
4.
4. Oh yeah, we have to super speed her. I'll tell you why. Because the river is pushing at 10 this way, right? We need for her to swim this. And she only has 4. She'll never get there, right? Even if she swims straight against the river, she's still going to end up going this way, right?
That's depressing.
So let's super boost her. How fast can she swim now?
20.
60.
Let's say 20. If she can swim 20, the river's not changing. It's 10 meters per second, right? If she can swim 20, she has to add her vector that way. Make sense? Okay, so find me this theta of VR. And I'll do the other one. What function are we going to use for this? Not for this one. What side is this? Opposite. What side is the 20? It's the hypotenuse. So we got a different trig function now, right? So if you do the inverse sine of 10 over 20, it should be, you get 30 degrees. Close. So notice how that's a little bit different. If I had done this better, I would have told you that Taylor could swim 20 meters per second because she's so crazy powerful. Her velocity, her resultant velocity would be here, and the theta for her resultant velocity would have been 26. Okay. But as her swimming and her river move back this way, her resultant vector is shorter, right? So it's going to take her longer to get across the river now. And this angle is slightly different than that angle because we've turned her from one of her, we've turned the resultant from a hypotenuse into a opposite side. Does that make sense? And the faster the river goes, the bigger that angle is going to get until it's the same speed as the river, and then it's like there's nothing you can do after that, which was the first example. Does that make sense? Kind of, sort of. Irene, you good? Okay. That's pretty much all I need you to be able to do for vectors. So I'll give you some more practice on it, and next day we will do, I'll give you a practice quiz. And I'll give you some time for your labs next day. So it'll just be like practice and data collecting and writing your lab reports and all that stuff. Yes? No. Practice just for practice, and then I'll do a real quiz for marks after that. Because I want to give you a chance to kind of see how I'm gonna do it, I haven't made a due date for the lab yet. Did I?
Keep it that way.
Did I make it? January? Darn. Did I write it down?
That's his idea.
Have you gone past your learning?
We're all learners in this classroom.
Oh.
I'm gonna pause that. Can we stop?